We will now talk about gravitational lensing, which is a very powerful technique to find about distribution of mass in the universe, whether it's visible or not. As you will recall from the general relativity, it predicts that the presence of the mass, again, whether you can see it in visible light or not, will distort the paths of the light rays passing by. Therefore, we have a method of learning about mass distribution regardless of whether we can see it on any wavelength. This was originally considered by Charlson and Einstein and also Zwicky, but it took until 1979 to find the first real example. This was measurement of a quasar, which turned out to have two images, which are just mirages. They're both the same quasar. And after that, hundreds, if not thousands, of lenses have been found. So the geometry is shown here. If we had a perfect alignment of the observer, the background source, and the lens, and distribution was symmetric, then each azimuth will be equal, and so the image of the background object will be now distorted into a ring called the Einstein ring. If we deviate from that symmetry, either by moving the lens a little bit in the lens plane or by changing the mass distribution to be asymmetric, the ring will break up and we'll see multiple images of a lens source. And this is indeed what's seen in case of multiply imaged gravitational lens quasars. So Zwicky already in 1937 predicted that gravitational lensing should not only be detected, but it can be used to probe mass distribution in galaxies in the universe, as well as to use clusters or galaxies as telescopes to magnify even more distant ones. And after all, it can also be used to test theory of gravity. All of those predictions have come true. As far as measuring masses using gravitational lensing, that took until 1990s and Hubble Space Telescope in order to be able to really do this well. These are Hubble Space Telescope images of a particular cluster that serves as a gravitational lens. All of these blue arches, arcs, and arclets are images of background galaxies that have been lensed by this cluster, split and distorted, and thus the cluster itself is essentially a gigantic lens in space that magnifies and distorts their images. From the distribution and shapes of these arcs and arclets, one can reconstruct the mass distribution in the cluster regardless of where the galaxies are. So the gravitational bending of light in general relativity is twice what you'd infer from Newtonian gravity. Most importantly, it is achromatic. Photons on any wavelength are deflected in exactly the same way. And this is unlike, say, lenses made out of glass. This adds to the power of the method because it's been used not just in visible light, but in radio and also X-rays. Obviously, the effect will be the strongest for the strongest gravitational field. And the strongest you can get is if you compress the lens mass into a black hole. Then you get maximum effect right at its Schwarzschild radius. But in reality, that doesn't happen. Most of the astrophysical objects like galaxies or clusters are vastly larger than their Schwarzschild radii, so the effect isn't quite as strong. Here is a simple schematic geometry shown. It's fairly obvious that there is observer, the lens, and the source in the background, and distortion of the light path, shown here as straight lines, but it's really a curve, can be represented as the angle by which between the direction to the lens and direction to the lensed image. All these angles are small, usually arcseconds or even fraction thereof, and so small angle approximations apply. There is some fairly straightforward geometry that then you can derive from here, and in the end, you have a quadratic equation that describes the deflection of light rays in this particular geometrical setting. We can simplify that expression a little bit by introducing a quantity called the Einstein radius. It's really an angle, angular radius, if you will, and it's given by this formula. Essentially, this is the characteristic radius in projection away from the lens where distortions will be strongest. And it need not be perfect circle, depending on the mass distribution. So the line that connects points that satisfy this criterion, regardless of whatever the mass distribution is called critical line. Generally speaking, for deflections within Einstein radius or thereabouts, you'll see multiple images. That's called strong lensing. For deflections further out, you see only distortions, but generally not multiply split images. That's called the weak lensing regime. So our quadratic equation is now shown very simply, and it has two obvious solutions. That this is high school math. And so in cases where lens isn't perfectly aligned, these two solutions correspond to two different images, one inside and one outside the Einstein radius. I mentioned different lensing regimes. If the deflections are strong in C-image splitting, that is called strong lensing regime. However, deflections will occur even further out. Obviously, the further out you go, the weaker the effect. But nevertheless, they'll be detectable in form of image distortions. And that's called the weak lensing regime. That turns out to be very important for studies of the cluster mass distribution. If you can map all of the distorted images, you can in principle reconstruct the distribution of mass that led to the lensing. This has been done on galaxies as well as clusters. With galaxies, we're talking about Einstein ring radii of the order of an arcsecond, so observations with Hubble Space Telescope were essential to do this. A particular group called SLAC's collaboration is one of them. They studied a fairly large sample of galaxies acting as lenses to some background galaxies that appearing as Einstein rings or segments thereof. And with some reasonable assumptions, they can infer the mass distributions in projection for the lensing galaxies. The results are shown schematically here for a handful of cases. The lines on the plots describe density distribution as a function of radius for visible matter, which is just measured stars, or rather mass in stars, for the whole thing that causes the distortion, and the difference, which represents contribution of the dark matter halo. As you can see, at smaller radii, visible material dominates, something we already learned from kinematical studies. As you go further out in radius, the dark matter component becomes inevitable and dominates the geometry. We can simulate the effects of gravitational lensing by taking an image of the sky, placing fictitious lens of given mass distribution in front, and seeing what it will do to the picture behind it. From that, we can then learn how to invert actual observations to derive distribution of mass that is doing the lensing. These are simulations, and you can see that clearly the effects are strongest in the middle and then get weaker and weaker the further out you go. This is another simulation used to illustrate this. Imagine that somehow there is a gigantic graph paper on the sky, and then you put a big cluster of galaxies in front of it. Then it will distort the geometry of the background as shown here. It is complicated because it's not a simple mass distribution. There are many different galaxies. Each of them acts like a little lens in of itself, and together they have also a collective effect. So inverting these geometries can be a very complicated business. Nevertheless, the method is well understood now, and a lot of good data have been obtained. Many clusters have been studied using this technique. Here is an example of a particular cluster where different contours show, say, average distribution of galaxy light, or the number density, or the inferred galaxy mass, or mass distribution for the whole cluster. This was done for quite a number of clusters. A small subset is shown here, and lensing gives a new independent estimate of the lensing mass in the cluster, regardless of whether it's baryons, or dark matter, or anything. As long as it's a matter of any kind that exerts gravitational pull, it will contribute. And remarkably enough, the inferred mass-to-light ratios for clusters are in excellent agreement with those we inferred from using virial theorem arguments from either X-ray gas or galaxy velocity dispersion. This is completely different physics and different kind of measurement, and this is why we believe that indeed there is some kind of dark mass there. We see its effects not just in kinematics of test particles like galaxies or protons or electrons, but also in manifestations of general relativity, the geometry of the images seen past the lensing mass. For this reason, people really believe that we are indeed dealing with dark matter, and it's not something like a distortion of gravity, because that will spoil gravitational lensing, and you'll never get the same result as you would for measurements using virial theorem. This is one thing, for example, that MOND cannot possibly reproduce. This kind of study is now done not just for big clusters of galaxies, but just in general deep field surveys where we measure a lot of faint galaxies, sometimes get measurements of their redshifts. What's shown here is a snapshot from one such survey called Cosmos, and what's shown on the left is the smoothed distribution of light that's observed in galaxies. What's shown on the right is the reconstructed distribution of mass in projection that is determined from the distortions of the images of galaxies in the background. Because they measure distances to galaxies, then they can actually reconstruct a three-dimensional distribution of dark matter in space. And the resolution isn't very good still, but here it is. It's actually remarkable that we can map mass distribution in space on cosmological distances in full 3 dimensions, even though we don't see the mass. This is likely to become a very powerful tool in our understanding of structure formation. Next, we will talk about gravitational microlensing. That's lensing of stars by stars, and it was used to constrain contributions of machos to the dark mass.